All right, so use calculus to find the minimum distance from equation y equals 4 on x to the origin and the coordinates of this point. So if we have a quick graph sketch, that's what we're trying to find, the minimum distance to some point, some random x value. So the coordinate, remember, is not just x, y, it's x comma 4 on x. That's the coordinate there. So now I want to know the distance between those points. So I know the distance between 2 points is y2 minus y1 squared over x2 minus x1 squared, which is 4 on x minus 0 squared plus x minus 0 squared. If I get the square root of those, I get 16 on x squared plus x squared, all to the power of a half. Now to find the minimum, I differentiate that. So again, the half comes out the front. I take 1 from the power, just multiply by the expression in the inside times the derivative of the inside, which is 16x to the minus 2, which would be minus 32 on x cubed plus 2x. All right, so there's my derivative of that square root function. If I tidy that up, and it's really important we tidy that up in a text-free environment, because I can rewrite this as, the square root of 16x to the minus 2 plus x squared, the negative square root of that goes on the denominator. I'll take my x cubed out the front, all right? The 1 on x cubed out the front, which means I can write the bracket in here as negative 32 plus 2x to the 4th. So once I've got it in that form there, it's really clear that the only way this derivative can be equal to 0 is if the numerator is 0, which means negative 32 plus 2x to the 4 has to equal 0. So that's the key. Just simplify the numerator as much as possible because the denominator can never be 0. All right, so if I do that, I'll get x is equal to 2. So if x is equal to 2, y is equal to 4 on x, which is 4 on 2, which is also 2. So the point occurs at the point 2, 2. And if I put 2 into my distance rule, I get a value of square root of 8. All right. Actually, it's worth highlighting, definitely worth highlighting that because our function hasn't put any domain restrictions, there's nothing to say that our graph doesn't go this way. Yeah. So in here, when I get x equal to 2, really it's saying x could be plus or minus 2. Yeah. And obviously you can see that I didn't quite notice that because until I check the answer. So yeah, square root of a function, even square root of a function, we get a plus or minus answer. All right, so in actual fact then, negative 2 is also a solution. All right. What about the next point? P is on the line 2x plus y minus 10 equal to 0, such that the length OP of the line segment from the origin is a minimum. Again, it's a very similar question, and they're regularly present on exam 1 questions. All right. So again, there's my line. Y equals 10 minus 2x. So the point P is given by the coordinate x, comma, 10 minus 2x, the y value. So again, if I use my distance between points rule, x2 minus x1 squared, y2 minus y1 squared, I end up with this expression. So I end up with 5x squared minus 40x plus 100. Take a derivative of that, I get 1/2 of that whole expression to the minus a half times the derivative of the inside, which is 10x minus 40. Again, let's get everything on the denominator where we can. So that square root of 5x squared minus 40x plus 100 goes into the denominator. Well, actually, that half probably is not quite written right, is it? That should be a 2 there. I've got a half out the front, which makes that a 1 on 2 like that. So that was a mistake, but we got away with it. and which means then the only way that this function can be equal to 0 is if the numerator is 0, so x has to equal 4. So if x is equal to 4, substitute x equal to 4 into the function. 10 minus 2x will give y equal to 2. And if I put 10 equal to 4 into my distance rule, I get the square root of 20, which is 2 root 5. All right. Rightio. This was a past paper question that caused all sorts of havoc. In fact, I think the students referred to it as the cone of death. Perhaps a bit dramatic, but anyway. A cylinder of height h centimeters is inscribed into a circular cone of height 12 and base radius 5. Determine the maximum volume of the cylinder. So it's really again, we want to get the maximum volume of the cylinder, yeah? So so the volume of the cylinder is given by pi r squared h. So I've got two variables again. Okay, so how can I get a relationship between the two variables? So what we need to do is consider the triangle that's inside this cone and how the variables that are in measuring the cylinder dimensions are related. So you can see that this right angle triangle of the cone has got a height of 12 centimeters and a radius of 5 centimeters because they're the dimensions of the cone that have been given. The cylinder itself has got a height of r and a height of h and a radius of r. So if we consider the similar figures, the similar triangles here, obviously that angle in here at the apex is the same. All right. And so all three angles are the same. So the triangles are similar. So we can set up a ratio here. Now you can set up the ratio in any way you want. I'm comparing the radius. So radius over 5 is equal to 12 minus h over 12. Okay, that's the way I set it up. I like to get my unknowns in the numerator. So I'm comparing small to big. So if I rearrange that now by multiplying by the 12 across, I get 12r on 5 equals 12 minus h. Add the h over, bring the 12r minus 5 across to the right-hand side, get a common denominator. I get h is equal to 60 minus 12r on 5. Maybe take the 12 out the front. I get the h is 12 times 5 minus r on 5. So there's my relationship between the two variables. So now, when I go to my volume is pi r squared times h. I left a big round bracket off there. So I get pi r squared times 12, or 12 times 5, which is 60. So if I expand that out, I get volume is 60 times pi r squared minus 12 pi r cubed over 5. When does the maximum occur? Differentiate 120 pi r minus 36 pi r squared on 5. Solve that. Well, actually, I took a common factor out just to make life a bit simpler. If it does, I took a 6, a pi and an r out the front. So I get 6 pi r on 5, 20 minus 6r. So that equal to 0 and r equal to 0, which is a nonsensical answer. We don't want a cylinder with 0 radius. Or r equal to 10 on 3 centimeters. So if r is equal to 10 on 3 centimeters, the height, substituting for the height will come out to 4 centimeters. So my volume, pi r squared h, will be 400 pi on 9 centimeters cubed. Probably didn't need to get the height, to be honest. Sometimes they ask for the dimensions, so I could have read through that carefully. We could have just gone and substitute our r value into our volume formula straight away. All right, so I reckon that was maybe 2009-ish. Yes, and students found it quite challenging. Okay, we have a rectangle, has two of its vertices, so two of its corners on the x-axis, and the other two lie in the parabola 16 minus x squared. Find the dimensions of the rectangle if it is to have a maximum area. So there's my parabola, 16 minus x squared. Two of the vertices on the x-axis, two of the vertices on the parabola. So because of the nature of our parabola and the fact that the y equal to 0 line is an axis of symmetry, we know that the distance across to the curve, while it's a little bit out on my graph, is the same distance. So if we think about the dimensions of that rectangle, so we have a total of 2x for the length. The height is the y value, which is 16 minus x squared. So area is length times width, which is 2x times 16 minus x squared, 32x minus 2x cubed. How do you get a maximum area? We'd find the derivative, which would be 32 minus 6x squared. X squared is equal to 32 on 6, which is plus or minus root 16 on 3, which is plus or minus 4 on root 3. So depending upon, there's my x coordinate, isn't it? It's either at negative 4 on root 3, positive 4 on root 3 are the two x values. What are we looking for? Find the dimensions of the rectangle to have a maximum. So I could get the length as well. I could put from here straight away, put 4 on root 3 into my area rule. Instead, I've got the length as well. So the length is 2 times 4 on root 3. So the length of my rectangle is 8 on root 3. The height is the y value coordinate. So if I work out the y value coordinate, I get 32 on 3. So then the area is length times width, which is 8 on root 3 times 32 on root 3, which I didn't really work out as an answer, which is going to be what? What is that going to be? 8 32s are 256 over 3 root 3. That'll do. Yeah? All right. What do we got here? The sum of two non-negative numbers is 16. Find the minimum value for the sum of their squares, the maximum value for the sum of their squares. Two non-negative numbers is 16. So x plus y is equal to 16. So therefore y is equal to 16 minus x. That makes fair enough. Whoops. The sum of their squares. So the sum of their squares means we want to add up each number squared. So I need the sum of x squared plus y squared. If I put y in, 16 minus x for y, I get s is equal to x squared plus 256 minus 32x plus x squared. So I get a quadratic there that I can differentiate to get 4x minus 32, which will mean that I get a minimum value when x is equal to 8. Substitute that in, y is equal to 8. 8 squared plus 8 squared is 128. So that's the minimum. All right. So if I have a look at the graph of that, what is it? The graph of 2x squared minus 32x plus 256, my maximums are going to occur at the endpoints. So clearly the domain of this function is if the two numbers have to add to 16, it means one can be 0, the other can be 16 or vice versa. Yeah, so the endpoints are at 0, 256 or 16, 256, which means my maximum possible value is 16 squared, which is 256. All right, nearly there, a lot of examples. And I'd like to go through, pause, read, watch, see how you go. Cross section of a drain is to be an isosceles trapezium. Of course it is. With three sides of the length 2 meters as shown. Find the angle theta to maximize the cross-sectional area. So it's a trapezium. So first thing first, we have to maximize an area, and the area of a trapezium is a half A plus BH. Yeah, so if I have a trapezium, A, B, H. All right, so it's the base lengths, top and bottom lengths times the height. So what do we need? So here's my drain over here. So I've got the A length here at 2, so that's okay. which means that length up there is 2, which means I need the little tails. I need that length there and that length there, and I also need the height. All right, so from this little right angle triangle that I can create here where the theta is, I've got a hypotenuse of 2. So if I might just come down here, hypotenuse of 2, angle, opposite, adjacent, and that's going to give me a sine theta and a cos theta for those measurements. 2 sine theta, 2 cos theta. So take it a step at a time. The A value is 2, the base is 2 plus 2 lots of x, and the height is height. So what was the x value? The x coordinate was 2 cos theta. So the base is 2 plus 2 cos theta. The height was 2 sine theta. All right, so I'm going to put that into the rule. So this is where it's easiest to miss a 2 here somewhere. Can I color code those 2's? There's 2. Oops, we'll go that way. Undo. We'll go A is 2, B is 2 plus 2 cos theta, H is 2 sine theta. So I get a half, which is out the front. A, the A value, which is 2, plus the B value, which is in yellow,